Quantum machine learning, revolutionizing complex data processing with future prospects. Imagine a world where complex data processing knows no bounds and machine learning algorithms can tackle even the most daunting tasks with ease. This is the promise of quantum machine learning, a field that's rapidly gaining momentum as researchers explore the potential of quantum computing to overcome the limitations of classical machine learning. But here's where it gets interesting. The pursuit of more powerful machine learning algorithms is continually pushing the boundaries of computational possibility, and quantum machine learning is at the forefront of this revolution. Researchers like Samarth Kashyap, Rohit K Ramakrishnan, and Kumari Jyoti from the Center for High Energy Physics at the Indian Institute of Science, alongside Apoorva D Patel et al., are investigating how quantum computing can be used to overcome the limitations currently faced by classical machine learning. Their work explored the theoretical foundations of quantum machine learning, systematically categorizing different approaches and critically evaluating recent developments like quantum-enhanced principal component analysis. This review highlights the potential for speedups in areas such as material science, but also acknowledges significant hurdles posed by current quantum hardware, including noise and scalability, and emphasizes the need for realistic benchmarks to determine where quantum techniques can truly deliver a practical advantage. Quantum machine learning represents a burgeoning field poised to revolutionize data analysis by harnessing the power of quantum computation. Researchers are actively exploring how quantum algorithms can overcome the limitations of classical machine learning, particularly when dealing with complex and expansive data sets. While still in its early stages, quantum machine learning demonstrates promise for accelerating certain computational tasks and potentially achieving results beyond the reach of conventional methods. One of the central challenges in quantum machine learning lies in efficiently encoding classical data into quantum states. Several encoding schemes have been proposed, each with its own trade-offs between circuit complexity and the number of qubits required. Amplitude encoding, for example, offers a more compact representation, minimizing the number of qubits needed but demands complex quantum circuits for data preparation. Researchers are continually refining these and other encoding methods to optimize performance on near-term quantum hardware. Beyond encoding, a key focus is leveraging quantum data directly, data originating from quantum systems. This requires a shift in perspective, moving beyond the structures of classical machine learning, and is becoming increasingly relevant as quantum sensors and error correction techniques mature. Recent theoretical work has established a framework for quantum learning theory, extending classical concepts like sample complexity to quantum realm. This allows researchers to rigorously analyze the potential benefits of quantum machine learning algorithms. While initial results suggest that quantum machine learning may not offer the dramatic advantage for all tasks, there are indications of potential polynomial speedups under specific conditions. Importantly, the field is moving beyond simply replicating classical algorithms, developing new quantum oracles, tools that allow algorithms to query data in a quantum manner, and exploring how these can be used to build more powerful learning models. However, the benefits of quantum machine learning are not universal. Computational advantages are strongly dependent on the specific problem being addressed. A practical path forward likely involves hybrid approaches, where specialized quantum subroutines are integrated into larger classical computational workflows. But here's the part most people miss. The broader utility of quantum machine learning will depend on overcoming technological limitations and identifying niche applications where its advantages outweigh its costs. And this is the part that sparks controversy. Can quantum machine learning truly deliver on its promise, or are we just chasing a dream? We'd love to hear your thoughts. Do you think quantum machine learning has the potential to revolutionize data analysis, or are there too many hurdles to overcome? Share your opinions in the comments below. Revolutionizing quantum machine learning. New Gaussian processes method. Here's a bold statement. The future of quantum computing might hinge on a mathematical concept that's been hiding in plain sight. But here's where it gets controversial. While neural networks have been the darlings of classical machine learning, their quantum counterparts are stumbling, and scientists are now turning to something called Gaussian processes to save the day. Could this be the breakthrough quantum computing needs? Let's dive in. The Los Alamos National Laboratory LANL team has just published a groundbreaking paper in Nature Physics, revealing a new path toward quantum machine learning. Their discovery? Gaussian processes, a mathematical framework long used in classical computing, can be adapted for quantum computers, potentially sidestepping the pitfalls that have plagued quantum neural networks for years. This isn't just a theoretical curiosity. It's a practical leap that could reshape how we approach quantum computing. And this is the part most people miss. Neural networks, the backbone of classical machine learning, rely on parametric models. These models tweak parameters to learn from data, enabling everything from self-driving cars to language translation. But when scientists tried to transplant these models into quantum computers, they hit a wall. Issues like barren plateaus emerged, creating mathematical dead ends that halted progress. As Martin LaRocca, a LANL scientist, puts it, we were essentially copying and pasting classical methods into quantum systems, and it didn't work as smoothly as we'd hoped. Enter Gaussian processes, a non-parametric approach that avoids these issues. Unlike neural networks, Gaussian processes don't rely on tweaking parameters. Instead, they use probability distributions, specifically the bell curve or Gaussian curve, to make predictions. Here's the kicker. The LANL team proved that this same bell curve applies to certain quantum computing processes. This isn't just a minor tweak. It's a paradigm shift that could unlock new capabilities in quantum machine learning. But here's the catch. Gaussian processes aren't a one-size-fits-all solution. If the data doesn't follow a bell curve, the predictions can go awry. To ensure accuracy, the team employed advanced mathematical tools to verify their approach, confirming that their method is both Gaussian and reliable for processing quantum datasets. As Diego Garcia Martin, the paper's first author, explains, this is the holy grail of Bayesian learning. It's not just math, it's a practical tool. Imagine predicting housing prices with increasing precision as more data comes in. That's Bayesian inference via Gaussian processes. And now we've shown it can work in quantum computing. This discovery marks the culmination of years of work and the first mathematical proof that quantum Gaussian processes exist. While quantum computers are still in their infancy, this research lays the groundwork for future applications. When powerful quantum machines become reality, researchers will need equally powerful machine learning models to tackle the world's most complex problems, from climate modeling to drug discovery. Here's the controversial question. Should we stop trying to force classical models into quantum computing and instead focus on building entirely new frameworks? Marco Cereso, the team's lead scientist, thinks so. We've been beating a dead horse by recycling old methods, he says. It's time to explore new ways of doing quantum machine learning. This paper isn't just a scientific achievement. It's a call to action for the quantum community. By shifting focus from neural networks to Gaussian processes, researchers might finally unlock the full potential of quantum computing. But what do you think? Is this the right direction, or are we abandoning classical methods too soon? Let's spark a debate in the comments. The future of quantum computing could depend on it. Paper details. Title: Quantum Neural Networks Form Gaussian Processes. Journal: Nature Physics. DOI 10.0138 S41567-025-02883-Z. DOL.org/Gaussian processes. DOI 10 Tekens 34-02883. Funding: this work was supported by the Laboratory Directed Research and Development Program, the Center for Nonlinear Studies at Los Alamos National Laboratory, and Los Alamos National Laboratory's ASC Beyond Moore's Law project. Breakthrough in quantum machine learning. New path discovered. Imagine a world where quantum computers could tackle problems that are currently unsolvable, revolutionizing fields like medicine, climate modeling, and cryptography. That's the promise of quantum machine learning. But there's a catch. Traditional methods just don't work as expected in the quantum realm. Researchers have been grappling with this challenge for years. but a groundbreaking discovery by a team at Los Alamos National Laboratory, LAN, might just change the game. On July 25, 2025, they unveiled a new approach that could finally bridge the gap between classical and quantum machine learning. This story begins with neural networks, the backbone of modern machine learning. These networks, composed of millions of interconnected nodes, have powered advancements in self-driving cars, language translation, and artificial intelligence. Naturally, scientists sought to replicate this success on quantum computers, which theoretically offer unparalleled computational power. But here's where it gets controversial. Despite their potential, quantum computers have stubbornly resisted the direct application of classical neural networks, leading to frustrating dead ends like barren plateaus, mathematical traps that halt progress. Enter the LAN team, led by scientist Marco Cerezo, who took a bold step back to rethink the problem. Instead of forcing classical models into quantum systems, they explored a non-parametric approach called the Gaussian process. Cerezo explains, "Our goal was to prove that quantum Gaussian processes exist, which could unlock entirely new ways of performing quantum machine learning." And they succeeded. By demonstrating that quantum processes can indeed follow a Gaussian curve, the familiar bell curve, they've opened a door to more reliable and accurate quantum learning methods. But what does this mean in practice? Let's break it down. Neural networks, while powerful, rely on tweaking parameters to learn, which often fails in quantum systems. Gaussian processes, however, sidestep this issue by focusing on probabilistic distributions. As Diego Garcia Martin, the paper's first author, puts it, this is the holy grail of Bayesian learning. It's not just a theoretical curiosity. It has real-world applications. For example, imagine predicting housing prices. With a Gaussian process, each new data point refines the prediction, making it more accurate over time. Now, apply this principle to quantum computing, and you've got a tool that can tackle complex, real-world problems with unprecedented precision. And this is the part most people miss. This breakthrough isn't just about improving quantum computing, it's a call to rethink our entire approach to quantum machine learning. Martin LaRocca, a quantum algorithm specialist, notes, "We were essentially trying to fit a square peg into a round hole by copying classical methods. This new approach shows we need to start fresh, designing models specifically for quantum systems." Published in Nature Physics, the team's paper, "Quantum Neural Networks Form Gaussian Processes," marks a pivotal moment in the field. While quantum computers are still in their infancy, this theoretical foundation ensures that when more powerful machines arrive, we'll have the tools to harness their full potential. But the journey doesn't end here. The team urges the quantum community to embrace this new direction, abandoning the old habit of recycling classical methods. Here's where it gets even more interesting. What if this approach not only solves current problems, but also reveals entirely new possibilities for quantum computing? Could this be the key to unlocking quantum supremacy in machine learning? We'd love to hear your thoughts. Do you think this new path will revolutionize the field? Or are there still hurdles we're not considering? Share your opinions in the comments. Let's spark a conversation about the future of quantum machine learning. Paper, Quantum Neural Networks Form Gaussian Processes, Nature Physics, DOI 10.1038-74567-25-0283Z. Funding, Laboratory Directed Research and Development Program, the Center for Nonlinear Studies at Los Alamos National Laboratory, and Los Alamos National Laboratory's ASC Beyond Moore's Law Project. Source, Los Alamos National Laboratory.